So let's first talk about the set of rational numbers Q. So what is a rational number? A rational number is any number that can be represented as a fraction of two integers. So we can write Q as m over n, where m and n are both integers. So why do we care about rational numbers? Well, it turns out that rational numbers have some sort of bad properties that we don't like, which is why we'll later turn to discussion of the real numbers. So the problems of the rational numbers is the so-called incompleteness. And the incompleteness of the rational numbers can be categorized into two kinds. The first is called the algebraic incompleteness. And what does that mean? It means that there are equations with coefficients in Q, but no solutions in Q, right? So there are some equations with rational coefficients, but no rational solutions. Well, for example, p squared equals 2. Okay, so it has no rational solution, and we all know that the solution should be the square root of 2. But the square root of 2 is not a rational number. Okay, so this equation p squared equals 2 has no rational solution. And it may seem pretty obvious to you, but as an analysis course, we have to do rigorous proof here. So our claim is that there are no rational p such that p squared equals 2. Okay? So how do we prove that? Well, for problems like this, like there are no such numbers such that blah blah blah, there are no such sequences such that blah blah blah, it is often difficult to prove directly, but it is often easier to prove from the opposite. So what do I mean by proof from the opposite? Well, our claim is that there are no such rational number p. But what if there is such a rational p? What will happen if there is such a rational p, such that p squared equals 2? And that proof is called proof by contradiction in mathematical term. So what we're gonna do here is what we're gonna prove by contradiction. Okay, so by writing out the by contradiction in front of the whole proof, we're telling our readers clearly that we're using the proof by contradiction strategy. Okay, so we're gonna assume there exists a rational p such that p squared equals 2. Okay, so this symbol, it is a reversed e, and it means that there exists. Okay, so what do we do next? Well, remember, the only information we have about rational number is that they can be written as a fraction of two integers. So we can write p as m over n, where m and n are both integers. And we're also going to assume that m over n is in lowest terms. And it means that they have no common factors. Okay, so why can we make this assumption? Well, because if m and n have common factors, then we can keep canceling out all the common factors all the way until they have no common factors, right? So what do we do next? So we're gonna plug in m equals m over n into p squared equals 2. So what do we get? M squared over n squared equals 2. So m squared equals 2n squared. So m squared must be an even number, right? Well, since n is an integer, n squared is an integer, so 2 times any integer is an even number. So m squared must be an even number. Okay, so since m squared is an even number, then m must also be an even number. And why is that? Well, because if m is odd, then m squared is odd, right? So since m squared is an even, then m must be an even number. So what do we know about an even number? Well, if m is an even number, then we can write m as 2 times some integer. So m equals 2k for some integer k. Okay, so then we're gonna plug in m equals 2k into m squared equals 2n squared. So we get 4k squared equals 2n squared, and which is n squared equals 2k squared. And you see, this equation is actually very similar to this equation. So by the same reason, n squared is even, and hence n is even. So we already have a contradiction here. And if you can't immediately see where it is, pause the video, ponder that for a moment, and I'll spoil it for you. Okay, here's the answer. Well, we find out that m is an even number and n is also an even number. So the contradiction is that if m is an even number, n is an even number, then m over n is not in lowest terms, right? And since we have already assumed that m over n is in lowest terms, so that's a contradiction, right? So contradiction. So this symbol right here is just a notation for contradiction, and you may sometimes find other people write this. So it looks like a horizontal line with an X, but it's actually 2 arrows pointing at opposite direction. But it's just a matter of notation. It doesn't matter which one you choose. Okay? So let's see what we have done here. So we assume that there exists such a rational p, such that p squared equals 2. and then we lead to a contradiction. So it means that our assumption is not true, okay? So what's the opposite of our assumption? So the opposite of our assumption is that there doesn't exist a rational p such that p squared equals 2. Okay, so this symbol, it's a reversed e and a slash, so it just means that there doesn't exist. Okay, so it's the opposite of a reversed e. Okay, so that's the end of the proof, right? Our claim is that there are no rational p such that p squared equals 2, and which is the same of the opposite of our assumption, which is this, right? And that's the end of the proof, okay?